And oh yeah, and then share screen. And then turn on the slideshow. Okay, can you see this random slide about the solubility of calcium carbonate? Okay, I'm assuming silence means yes. Oh, awesome. Thank you. I've got my chat up so I can see now. Go ahead and chime in whenever you want. This is a random slide here because the previous lecture was supposed to get into how you solve these systems of equations where you have speciation of different kinds. Here's gaseous CO2, there's aqueous, so this is dissolving in the water. This is calcium carbonate just dissolving, but then you get into this species of dissolved CO2. So that's what these guys are. Here's pH. All right, so we've been solving systems of equations that describe, hydraulic head or concentration at all these different nodes in a domain. If you were going to run a reactive transport model where you allowed minerals to react or aqueous species to react, then you would start to have this other system of equations that also needed to be solved. And so anyway, I will talk about that last Tuesday as soon as I get it recorded. It's a very different kind of modeling. But particularly the students who come in from more the high temperature geochemistry, it's kind of interesting to see how those models actually work, how you could calculate equilibria between water and a suite of minerals and some additional dissolved species. So anyway, that will be last Tuesday's lecture. This lecture is about running complicated modeling software. All right, and there are plenty of ways that it can get complicated. One way it gets complicated is instead of our nice simple individual equations, the equations become nonlinear. And I'll give you a good example of that, this lecture that used to be a homework for Geology 775, but I only did it 1 year when I had some people who were like really into it. So we're not doing it this year. I want to talk about coupled equations because that's just really important in a lot of areas. I mean, if you want to do geothermal convection, you've got to simulate heat and groundwater flow. If you want to simulate coastal groundwater flow, you have to deal with density gradients between salty water and fresh water, which affects flow. And then the flow affects the concentration, affects the salinity, right? So these things are tied together, they're coupled. So we'll talk about how you do that. And then we're also going to just investigate a set of scary equations, right? And talk about what makes them scary. Because once you can identify exactly what's making them scary, sometimes it helps you break it down so you can approach them more easily. And I'll show you how I do it. When I get a new code, somebody says, hey, we're going to simulate this. I'm like, okay, I need to know what the governing equation is. It's like, I don't even know what that governing equation is. So how do you do your detective work to figure out what's going on? So let's jump in. All right. So let's say you wanted to simulate heat conduction through, I'm moving stuff around so it's not over my screen, through iron, like an iron rod or an iron plate or something at low temperatures. Okay, and I have that exclamation point there because of course you want to simulate heat conduction through an iron rod. Everyone wants to do that. Okay, so maybe you're working in the semiconductor industry and you actually do need to simulate heat through some kind of metal. All right, so what I have here is a nice one-dimensional heat conduction equation. And we've gotten a little fancier. Instead of just putting the diffusivity here on the diffusion term, we have the thermal conductivity and we have the heat capacity over on this side. So this is slightly fancier than the one we've been using, but this is a pretty standard equation. It looks just like the equations we've been solving all semester. Right? Now, what's new here is that the thermal conductivity Depends on the temperature. So as you're solving for the temperatures will change. The thermal conductivity will also change. So let's think about that. First question is, how much will it change? And this is what I mean about low temperatures. Here's, so freezing is what, 273 degrees Kelvin? So here's freezing and here's absolute zero. And look how the thermal conductivity changes. And we know this also about superconductors and things. Their electrical conductivity changes. I don't know what happens to their thermal conductivity, but it's not, we can kind of cope with the idea that properties of metals could change at these really low temperatures down here. All right, and it varies by almost 2 orders of magnitude. It's a pretty big variation. All right, so I've got this. So this means here's our same equation, but I've said explicitly here that kappa is a function of T. So we have some kind of just internal coupling inside this equation, right? So we don't know what the hydraulic or what the thermal conductivity is until we know what the temperature is. But we don't know what the temperature is until we know what the thermal conductivity is. So what do we do? All right. The first option is that you iterate. And this is going to apply to things that we talk about later in the class today. So make sure that this sort of settles in some way in your head. All right. What you do is you start with your initial temperature, whatever it's going to be, whether it's legitimately initial conditions, or you all just wrote a code where it was steady state and you started with an initial guess. Whatever you start with. And in fact, you have already iterated to find a solution. And that again was for steady state. And this is going to be transient. But it turns out you all already know how to iterate, which is really cool. Okay, so you start with your initial temperature and you're like, well, I know what the temperature is, so I can calculate the thermal conductivity. So you calculate that your first time. On your next time step, right? Well, you calculate the temperature at the new time step. And then you go, oh, I have a new temperature. Okay, so I'm going to calculate a new thermal conductivity. And then using that thermal conductivity, I'm going to calculate the temperature again and see if it changes. I should have deleted this part because calculate temperature again and then see if the solution has converged. Okay. And you already know how to check for convergence because that's what you did in homework 8. You compare the temperature from here with the temperature from whichever one was previous, either your on your initial thing, it would be the, you calculated here. You compare it with that guy, okay? Oh, yeah, that's what I wanted to point out, is that if it's the first time through, you compare it with step 1. If you've already gotten into the iterations, then you just keep running through here and you compare this temperature with the previous iteration, right? And that's what this marks is if the change is too big, you just repeat steps 2 through 4 until the change is small, that is, it's less than the tolerance, and then you're good. So this is iterations written out on the page, right? And as I say, you all have already done this, but you didn't have to calculate so many things in between. You just calculated the hydraulic head and then compared it with the previous version of the hydraulic head and just looped through that. This adds an extra step because you calculate the temperature, then you calculate the thermal conductivity, then you calculate the temperature again. Now, these things normally do converge, but sometimes they don't. All right, if you give it a hard problem, they won't converge. So let's think about what you would need, what your code would ask you for, right? It's going to want to know that tolerance so that it knows whether it's close. And it's also going to ask for a maximum number of iterations. And this is just a practical thing, because if you tell your code that it can do 100 iterations on each time step, it's going to take a long, if it needs all 100 or it needs to get close to 100, it's going to take a long time to run. It's like running each time step 100 times. And the other thing is that often, like in my experience with groundwater codes, if it doesn't converge within about 20 iterations, it's not really going to. It's one of those things where it's like alternating between peaks or something in the solution. So that's my default number of maximum iterations is 20. And I'll tell you another secret here is that often the problem is the first time step. Because that's when you're starting at initial conditions, you've just imposed some new boundary conditions. Often things are changing quickly right then. And if they change too much, it's hard for the solution to converge. All right, so, so the secret is usually to make the time steps smaller. Sometimes you just need to try different initial conditions. So these are your two go-to things to do if the solution doesn't converge. I should add another one in here. Actually, let me do this right now. I'm going to pop us out and add this. Oh, here we go. I need to add, make the tolerance larger, because sometimes it legitimately takes forever to get to a tolerance that's really tiny. So let's pop that back open. We need to add that one. Play with the tolerance. Sometimes you can learn a lot about what's going on if you just make the tolerance larger. Okay, questions about that so far? Seem reasonably straightforward? Okay, so iterating is the most common thing you'll come across. But you will also potentially come across the predictor corrector method. All right, so let me take you through this one. It has some advantages to it, and we'll get to those at the end of the slide. Let me just tell you what you do. Now, I know this whole semester, we've been starting at time step k-1 and moving up to time step k. And I remember it being confusing back in the day when somebody said, hey, well, let's start at time step k and move to time step k+1. And you wouldn't think that would be confusing, but it just shifted my entire frame of reference. I was like, no, what do I do? Okay, but for the predictor corrector, we really need to be able to think of stepping forward in time. It's weird to step from time step k-1 to time step k-1/2. It's just weird. So work with me here in thinking forward. This is our current time step, and our next time step is k+1. So what you do is, we know the temperature at the current time step. We know we can calculate the thermal conductivity at this time step. All right. What we're going to do, in fact, is we're going to first do this predictor step. And in this step, we step from k to just halfway, k+1/2. All right. Now, you use an implicit time stepping scheme. This is the, you know what that one is. That's the backward difference. All right. And you know that it can be more or less accurate depending on different things. I'm not going to get into the reasons why you use a different one here from there, but numerically it works and you would find the references and move on. Okay, so you use an implicit time stepping scheme. You calculate the temperature at time step k+1/2 using your previous temperature and your previous thermal conductivity that you had from your previous time step. Okay, next, you update your thermal conductivity using the temperatures from time step k+1/2, right? So we start at time step k, we step forward a half a step, and we calculate temperature only so that we can update the thermal conductivity. All right, now, don't update T old at this step. We want T old to still be the time at the previous time step. Okay, so update the thermal conductivity, but don't update the temperature. Right, the corrector step is you step all the way from time step k to time step k+1 using your Crank-Nicolson time stepping scheme and your new thermal conductivities. So this whole predictor step is just a way of updating the parameters and then your parameter that's varying, right? And then you just do a regular, this is like a regular simulation step. It's just you're using an updated thermal conductivity. All right, so at the end of the time step, you update thermal conductivity again, because this is this, right? This is about to become time step K for the next stepping to time step K plus 1 spot. All right, so you update the thermal conductivity again using your new temperature that you calculated, and now you update T old so that you're completely ready for the next time step. You've just updated what's about to be T at time step K and thermal conductivity at time step K. So you could start the next predictor step. Okay. So overall, you don't need to remember all the details of this. You need to remember that you know where to find this in your notes, and that predictor corrector means you start at one time step, you go halfway, calculate whatever you need to so that you can calculate the parameter that's going to change. And then you go back and you jump all the way to the next time step using those parameters from the middle of the time step. Guys, okay with that one? Okay. Let's go forward on this then. Good thing I put this on here. The cool thing about predictor corrector is that it doesn't require a tolerance. It doesn't need a limit on the number of iterations. You may need to have slightly smaller time steps, but it's going to be more efficient than iterating very often. All right, you might have to do 4 iterations, but if you can do this in one predictor corrector step, that's only 2 solutions per step, as opposed to 4 iterations per step. So anyway, it's a way to have, it can be a little bit more efficient than iterating, right? Iterating is still the most common one that I see in the models that I use. But predictor corrector is kind of cool. Okay, so you have 2 options for this. All right, and now let's think about coupled equations where basically you have an equation where some parameter changes with time. So you're going to have to update that. But the reason it's changing is because you have a whole other governing equation that you're solving at the same time. And the 2 equations are coupled together. All right, so this is an example of that, geothermal convection. And let me see if I can move this around again so that we can see more of this. Oh no, I cut off the horizontal scale. I'm sorry, these are, tens of kilometers across. All right, imagine these being, wait, I have to move this one more time. Okay. Imagine these being carbonate platforms. All right, so here's the bottom of the ocean, here's the continental slope coming up the carbonate platform, and here's the top of the carbonate platform. This can be anywhere, carbonate platforms, the small ones are, 10 kilometers across here, and the big ones are like Florida, right? The part of Florida that sticks out is only half of the top of the carbonate platform, right? The other half is the wide continental shelf that sticks off into the ocean, right? And in fact, what you're seeing here are flow lines that come into the carbonate platform on the side and then exit at the top. And a lot of flow is focused here toward the center. And if you know about the blue holes on the west coast of Florida, those are thought to be places where geothermal convection, fluids that are participating in geothermal convection, are exiting. So just to remind you what's happening here, here's a normal geothermal gradient, almost normal geothermal gradient, right? Where the temperature increases with depth as you get below land surface or below the seafloor. And that's because we have heat flow coming from the center of the earth coming up here. So if we were going to set the boundary conditions for this temperature, we would specify the temperature here. We know the temperature of the ocean approximately. We know the temperature at land surface or at the surface of the ocean, approximately. If we have oceanographers in the room, you know there's a thermal climb, the temperature declines with depth. All right, so we know the boundary condition here. We know there's a heat flux, a specified flux across the bottom. And so those are the thermal boundary conditions. The hydraulic boundary conditions are that we know the hydraulic head across here, or we usually simulate pressure because you start dealing with density. If the density is constant throughout the whole thing, then it's perfectly fine to use hydraulic head. But we know what it is, right? We know what the water, how deep the ocean is. We could calculate the pressure, or we could just specify the hydraulic head. Sea level, right? So what's happening here is that cool seawater comes into the carbonate platform where it gets warmer and warmer and warmer, and what warm things become less dense, or at least warm water becomes less dense, and so it rises. There's a density gradient between this cold seawater and the warm pore water inside the platform. So that's what draws this in. There's a density gradient, pulls things in, these things get warmed up, and then they rise. So that's geothermal convection. What's happening here is that these thermal contours are pretty much conductive until you get over here and you see all this flow concentrated in the center of the platform. There's so much of it and it's moving fast enough, and you can tell how fast it moves by how close the streamlines are to each other. So this is the fastest place in the simulation. What's happening is it's carrying warm water up fast enough that it's heating the areas up above. Basically, this warm water is moving really fast and it warms up other parts of the carbonate platform. So this is that situation where the groundwater flow wouldn't be occurring if there weren't density gradients. The density gradients depend on what the temperature is. And if you get enough flow, that perturbs the heat, the temperature field. All right, so groundwater flow depends on the temperature because it depends on the density, and the temperature depends on groundwater flow because you can move heat around if the groundwater flows fast enough. So these things are coupled together. And this is an example, the bottom one here, this permeability is a little lower than you would see in like coastal fine-grained sands. So they're saying this is a fine-grained kind of a situation. All right, here they've increased the permeability by an order of magnitude, and look at the effect on the temperature. Now you're moving all this cool seawater in. You've cooled this platform off a lot. See, here's the 50-degree contour. There's the 50-degree contour. Here, this gets down to 100 easily, right? Now the 100-degree contour is way over here. And we're moving a lot more heat up this way, right? We've got a real bend in these things. And this whole part of the platform is really being cooled a lot. So anyway, that's an indication of how groundwater flow and heat transport could really interact to make geothermal convection. So these things interact. How do we deal with that? All right, so this is just a recap of what we just said, that the groundwater flows because of density gradients. The density depends on the temperature, and then the temperature depends on the groundwater flow. So this is how this system is coupled, right? And it turns out that what you do is exactly what you did with the individual non-linear governing equation, which is just, you can iterate is the big one. I don't see predictor or corrector as much with this, but iteration definitely. Let me check and see whether I wrote out what we did or whether we need to talk it through. We were going to talk it through. Okay. Should I go back to the, I'll go back to the previous slide so we can see this, and then we can think about what we would do on the new time step. Okay, so we remember we need to solve the groundwater flow equation. We need to update the density. Then we need to solve the heat transport equation. And then we need to do some more things so that we're iterating. So, I'm going to pop us out of here so we can actually write on here. All right. So, what do you think I should do first? How did we start the iterations with the last one? Did we start by solving for, we were doing temperature and the thermal conductivity. So, and the first thing we did was we solved for the temperature, right? So should I solve a governing equation to start with? Or start with some initial conditions?
Yeah, I suppose you would start with some initial conditions first.
Actually, that's a good idea. Okay, so start with initial conditions. Or I'll just say, or a previous time step. All right, and let's see, what would we know from that previous time step? We would know the hydraulic head. We would know the fluid density, right? Groundwater density. And what's the other thing that we would know from that previous time step? Sierra, we're solving for coupled groundwater flow and heat transport. And we've just said that we know the hydraulic head, we know the fluid density. What else do we know? We do know initial conditions and boundaries. That's sort of part of the original setup. So we'll say we know the initial conditions.
Do we know the starting temperature?
Yeah, we know the temperature. Excellent. Thank you. There we go. We know the hydraulic head, we know the fluid density, we know the temperature from the initial conditions or from the previous time step. Okay, so the next thing we need to do is we need to start doing something with the new time step, right? What do you think we should do?
I mean, at this point, would you solve the governing equation?
Yeah, that's what I was going to say.
Good. Yeah. I like to start with the hydraulic head. So let's say solve for the hydraulic head. All right, so we've just updated the hydraulic head. We don't have any new information about the temperature yet, so we don't want to update the fluid density yet. What should we do next? We have new groundwater velocities. Could we use that for something? So the heat transport equation is like the solute transport equation in that it has three terms. It has the change in temperature with time, and it has the conduction term, the dispersion term, and it has one other term. What's the third term in the heat or solute transport term or equation?
Yeah, the velocity.
Yeah, it's the advection term. All right, so we know we need to have some velocities to put into the heat transport equation. We just solved for the hydraulic head, so using Darcy's law, we can figure out what all the velocities are. So should we solve for temperature now?
Do you have to update the velocities? in the
Ooh,
equation though?
that's a good one. You're right. Update velocities. Excellent. Now could we solve for the temperature?
Yeah.
Yeah, we can solve for the, oh, my chat window has people off the bottom. Yeah, there we go. Solve for the temperature. And then what do we want to update now that we've solved for the temperature?
Or the, oh, I don't know.
Let's look at these three things. These are the things we knew at the end of the previous time step. We've just updated the hydraulic head. Then we're going to update the temperature. What else do we need to update?
I put it in the chat, but fluid density?
Oh, thank you. Yes, you are right. Yes, what Erin said, definitely. Update the fluid density. I'm sorry, I can see the chat. I just don't actually read it. Okay, cool. So we'll update the fluid density, and then you've got enough stuff. Now that you've updated the fluid density, what you're going to do is start that iteration thing. You're going to solve the hydraulic head again, right? And then you're going to do your check to see whether you need to go back and solve for the temperature and update the fluid density or all these things, okay? So check your tolerance or check results compared to tolerance. And if you pass, you're done and you move on to the next time step. If your differences are still too large, they don't, your answer hasn't converged yet, then you need to calculate the fluid density and go back. Oh, no, then you update the velocities. You come back to here and go back through there. All right, so let's draw a little arrow right there. I wonder if that one will do. That one will probably do. No, this one's not going to work, but here we go. Ah, here we go. Once I get this approximately the right size, then we can just rotate it. And oops, scooch it in here. All right, so eek. So you check your tolerance. If you need to go back, you go back up here, you update your groundwater velocities, solve for temperature, update your fluid density, come back around, all right? And once you come out all right, then you can move on. I should add that we know the hydraulic head, and we should put groundwater velocities. We can calculate these easily from the hydraulic head. Okay, you all reasonably happy with that? Okay, cool. Let's get back into our, oh, let me save this. And then we'll get back into our slideshow. There we go. So that was cool. Made some progress, and that it does have a few extra layers, but it's basically the same. All right, so what I wanted to talk about now is just scary equations, okay? Because we've all seen them. Yeah? Okay. So, so I went through the sutra documentation and I found the governing equation for groundwater flow, and this is what it looks like, right? So let's just look at it and like think about what makes it so bad, right? Okay, what are some things that just make this equation completely perplexing? pop this open too so that, oopsie, here we go. Yes. What are all those variables? That's usually the first way in which these things are just awful, right? I see some other things like here, this term, I mean, for us, where it's using gradients and that's fine, but I know that when you first start, just even having it written in 3D as opposed to 1D is kind of, it's a lot. All right, so let's add this, it's 3D. Now this is a groundwater flow equation. So we're used to thinking of that as the diffusion equation. How many terms does ours usually have, our groundwater flow equation?
Just 3.
Well, ours usually has 2, right? The S sub S side with the DHDT and then the hydraulic conductivity. Yeah, our transport equations always have 3. But like our groundwater flow equation, our groundwater flow equation only has 2 terms. And this 1, 2, 3, we might guess that that's a source term. So having 4 terms isn't really the end of the world, but it's, God, there are 4 terms. It's 3D, there are dells, and it's has lots of terms, more than we're used to. Okay, well, I tell you what, that's a pretty good list of these things. So let me at least take the mystery out, and this is something you do when you get a new code and you're like, yeah, what are all these things? You look, they always explain what the variables are. So what I usually do is I just make myself a list. So let's get back into here. All right, and this is what these things are. All right, so SW, I'm just going, from left to right in this equation. What's SW? Ooh, that is the saturation. All right, that's how much water there is in the pores, because there could also be air. So what's the fraction that's water? So this goes from 1 to 0, completely filled with water, saturated, to 0. The air is all that's in the pores. Okay, so we're talking about unsaturated flow. The water table can move up and down. And we might be, if this is less than 1, then we're above the water table. All right, so that's a reasonably simple concept. We can maybe work with that. Let's see. Rho is the density of water. Okay, we can work with that. That's a familiar symbol. Okay, SOP, you got to read the sutra documentation. It's the specific storage pretty much divided by rho g. They, Cliff actually derived it. I say that he derived it wrong. And in my versions of sutra, it actually is the specific storage divided by rho g. If you read the sutra documentation, you'll be like, that's not the specific storage, but it's close enough. He's never bothered to change it because it's close enough. Okay. So then what's this weird eta thing? Well, it turns out that's the porosity. So whenever I come across something like that, I take the original governing equation and I rewrite it using the variables that I prefer for this, for whatever we're describing. So you'll see I'll switch it from this eta to the phi that we're used to using. All right, so we'll take care of that. That's density again. This is the change in water saturation with pressure. I'm going to discuss that in a minute so you see what that's for. What it says is that there's, well, I'll show you a picture. It'll be clearer. Okay, and this is dp dt, okay? P is pressure, and I just want to remind you that we can get from pressure to hydraulic head this way. The hydraulic head is the pressure divided by rho g, that's the water density, plus the elevation relative to the datum, wherever you're measuring from. So So we know we can convert this to hydraulic head. So, okay, that's useful. That means that this is essentially our dH/dt term, which we kind of expected because there was something related to the specific storage. So this, all of a sudden, we can tell is going to be our specific storage term, our change in mass with time. All right, what's this next one? We've got the porosity times the water saturation. And I'll just tell you right now that if you're thinking about doing a mass balance and you want to know how much mass of water is in this pore volume, you need to know what the porosity is. And then you need to know how much of that porosity is occupied by water. So that's why you're seeing the water saturation show up so much. And in this term in particular, what's the mass of the water here? Now, the issue is that the density of the water can change with time. So this is the change in the density because of something, all right? And in this case, in Sutra's case, you can simulate either solute transport, and if you're simulating salinity, that would affect the density of water, or you can simulate heat transport. And we just had a great example of how heat could affect density, and that could affect groundwater flow. So that's what this term is all about. This is all about density being variable. And this is where this groundwater flow equation is coupled to whichever transport equation you're using. If you're transporting something that doesn't affect the density of groundwater, you just make this be 0 and this term just goes away. But if you're transporting heat or you're transporting salinity, then this is non-zero and you keep this term. So this is another reason this equation is awful, is it says, hey, I'm coupled to another equation. That's why it isn't as simple as the groundwater flow equation that we've been using. So that we can add that to another list of reasons this equation seems awful. It's like, oh, it's coupled, I have to deal with coupling. Okay, the next thing here is, now this is the permeability tensor, this little k with the 2 underscores. And you might remember that we can calculate the hydraulic conductivity for that. That's the fluid density times gravity divided by the fluid viscosity, that's a mu, times the permeability. Okay, so we can tell that this relates to the hydraulic conductivity. And in fact, look, there's rho and mu. This is very close to the hydraulic conductivity. This is like the hydraulic conductivity divided by G, right? And it's also multiplied by this other thing, this Kr. Okay, so what's Kr? Kr is the relative permeability in unsaturated media. Just like I'm going to talk about this dsdp term, I want to talk about this Kr term in the next few slides. Okay, we already said that mu is the viscosity, and Q, we were right, that's a source term. We can work with that. I want to add one more note that I didn't discover until I was simplifying the equation. They've put underscores on things to indicate that they're vectors, right? So this is a gradient of P, so it's a vector. They've indicated carefully that G is a vector here. And I'll just tip you off that that's because they only want this extra term in one direction, the vertical direction, okay? Because gravity only points one way. All right, it points down and we want our vector to point up, which is why this is negative. All right, but there's no gravity in the horizontal direction, so this term goes away in the horizontal directions. It's not satisfying, but that's how people write this when they write the groundwater flow equation in terms of pressure. Okay, so let's move on to making this equation look better, because you get one of these codes, you know you have to use this equation, but it just feels comforting if you can get to your equation from their equation. So that's what we're doing here. All right, so simplifying. Here's their equation. The first thing I'm going to do is just say, hey, let's make saturation be 1. All right, let's say everything's fully saturated. Then a bunch of things go away, right? This is 1. This is 0. It doesn't change. It's just 1, right? Let's see. So this first term becomes rho times SOP times dPdt, and we can convert that. If we multiply by or divide by rho g and add whatever, right? We get rho S sub S dH dt. Okay, that's good. That's pretty close to what we're used to for our left-hand side of the groundwater flow equation. Still have this extra density, but we knew that was sort of floating around in there. Okay, here's this source term. Now it's just the porosity, and look, I used our symbol instead of his symbol, times the change in density with respect to either the concentration or the temperature. This side, I said, hey, let's make this be the hydraulic conductivity divided by G. Oh, because this relative permeability becomes 1 if things are fully saturated. So we just got rid of this guy too. So we did this. And I converted this to hydraulic head. This entire term can just be, if you do this, converted to grad H. Okay. Now this is starting to look more like our regular equation. If we convert this guy here, and now let's just get rid of the density. Let's say that the density is constant, which means it can move out of this gradient. It's out of the spatial derivative. If the density is constant, it can go out, and then we can just divide through. Okay. So, oh, and I forgot, if the density is constant, and we just conveniently forget this term entirely, which I did, all right, you wind up with our standard groundwater flow equation, all right, because these G's cross out. We got rid of the density because we assumed it was constant. This simplifies nicely to a form of the equation that we can work with. It is still allowing us heterogeneity, right? But we talked about that before. We can cope with it, all right? So I hope I've convinced you that we can get from this complicated form back to our form. And an interesting thing about the way we did this is it let us know the things that they're allowing, right? If we started with ours and went back up, we can see that they're allowing the density to vary, which we have to if we're going to couple these things to a transport equation. All right, and they're allowing the saturation to vary, so they can simulate flow above the water table. All right, I do want to tell you how you can deal with terms like this, the change in water saturation with pressure. As the pressure rises and falls above the water table, the amount of water in the pores changes. Okay, and this one, as the amount of water in the pores changes, you might guess that it's like having other stuff in the way in the pores. So the permeability that the water sees would be lower. I mean, it's moving through a smaller area of the pores. It can't go through the whole thing. It moves through a small part. Well, the permeability is going to be affected if you do that, right? So that's this relative term. So let me talk to you about how these are handled, just so you know that if you have this kind of a term in an equation you're trying to simulate, how you would deal with it. And if you get into environmental consulting, you might actually be using this an equation that lets you move above the water table, depending on what you're doing. Okay, so, all right, what do you do with all the nonlinearities and coupling? And I underlined them. Here's this first term, this change in saturation with pressure. Okay, this comes from the retention curve, and I'll show you that on the next slide, or in the next few slides. This is supposed to be KR, but I covered it up with this by accident. So it's this K sub R. It also has an empirical curve, all right? So you can imagine if your code is coming along and you've just you've just solved for the pressure. Now you need to calculate these empirical terms, right? I know what the pressure is, so I need to know what the relative permeability is. And now I need to know what the saturation is. So these are things you would update once you knew what the pressure was. And you'd update them by looking them up on these empirical curves. Okay. Now this I'm just pointing out that this d rho du, assume that that's just a number. All right, so you just type that in. Sophia, for your information, that is 0.715 in your modeling. All right, and you would laugh if you use Sutra. Yes, because they name this. This is one of the other things that happens in codes, and they've gotten a lot better since they usually have graphical user interfaces, and they just say enter the density. Now enter the density of the sediment grains. They actually use words to tell you what they're after, but sometimes they still use their internal variable names. You know how we named all our crazy stuff inside our codes? We said the concentration of the previous time step was C old, right? Well, you can name it whatever you want. The guys in Sutra named this because inside the code, rho is starts with an R. And this they convert to W for some reason. So, oh no, sorry. They call this rho W, RHOW inside the code. So their variable name for this term is DRWDU, right? DRWDU. And it's just this 5-letter variable name, right? So these are the kinds of weird, obscure things that as you get to know a code, you'll start to realize what they are. And why did they name that DRWDU? That doesn't make any sense at all to me. Well, it's this number, okay? Okay, so they assume it's a constant. We know that these things might not be constants. As you change the temperature of water, you don't always get the same change in density depending on what temperature you're looking at. But for purposes of Sutra, it's close enough. Situations you would meet in the real world, it's close enough. Okay. I am checking. Oh, we're doing fine. I don't have a, clock that I can see. Okay, so we talked about that one. We need to get the rest of this guy, and we know how to do that. We just solve the heat transport equation or the solute transport equation. And in Sutra, they couple it using iteration. So you all actually know how to do this. And if you were new to looking at the Sutra input, you had a new graphical user interface to use Sutra, you wouldn't be surprised now to know that it would want to have a tolerance, and it would also like to have a maximum number of iterations, okay? So that's how you handle these. These are the nonlinear terms here, and the coupling that comes in here. All right, and now let me just tell you a little bit more about these nonlinear terms. Oh, it's already 11 o'clock, and I wanted to talk about one other thing. So I'm going to leave this slide here. You can check it out. It's really cool. It talks about the curvature of the interface between water and air. And we've all seen water. I mean, just you get a drop of water between your fingertips, and you can see the curve of the water. And if you pull your fingertips apart, you'll see the curve get more curvy, and then it'll break. And you'll just have 2 wet fingers instead of a little meniscus of water. We've all seen the curvature when you measure water. Yeah, you take chemistry, right? And you've all seen at the edge of the beaker, the surface of the water curves up, and you're supposed to measure it, et cetera. So this describes the fact that the surface of water is elastic, right? And it wants to be absolutely flat if there's no pressure gradient. To make it bend, there has to be a pressure gradient, right? So if you had a capillary tube, you'd be pulling the water up and the surface would bend down, right? And when you water a plant too much and you have a dish underneath and the water bulges up, right? You get this angle. Anyway, it's fun talking about capillary stuff, but that is the hydrogeology class and not the numerical modeling class. So this is fun. You can calculate the difference in pressure across this interface depending on what the radius of curvature is and what the surface tension is. but we'll move on. We've already defined the saturation. All right, I'm just pointing out because later I have another equation. I'm not sure we'll get that far, but this is an equivalent thing. It's called moisture content. It's just the saturation times the porosity. It says how much water is there in the bulk volume, whereas this is just how much water is there in the pores. All right, so this is measured a lot like the porosity. We'll move on from that. This is what I wanted to show you, is retention curves. All right, the soil moisture people don't want to use pressure. They use this guy, which I can't even remember what that one's called. Psi, I can, it's psi. Okay, so think of the pressure declining as you go up, all right? And here is the moisture content. So think of this being the saturation. Think of it being 1 here, fully saturated, and 0 here, completely no water left. All right, and what this is just showing, this is a fake soil, all right? An idealized soil, I don't know what it is. It's a bunch of capillary tubes of different widths. And that's a reasonable approximation of soil because soil is a bunch of capillary tubes of different widths. They're just a lot squigglier than these idealized rectangular ones. All right, and if we start with everything fully saturated, we have this first picture here. So the black is the water, and these things are the walls of the capillary tubes. All right, now we're going to start draining the water out the bottom of these things. All right, and the first thing that happens is you start to get more of a pressure gradient, right? We're pulling the water down. This is under tension, so it bends down, and there's not so much water in it anymore. This bends in just ever so slightly. All right, so the pressure declined, and there's a little less water in our system. Okay, if you keep pulling, these big ones are the ones that break first. The smaller capillary tubes, you know, they can pull water up higher. That means they can survive more tension, right? So these wider ones are the ones that empty out first. So you start to lose water from the biggest pores. So we finally hit a place where we broke these little meniscus, one of the meniscuses. I'm not sure what the plural is of that. But what happens is here one broke and you start to, there's a lot less water in this whole system on average all of a sudden. All right, and we call this the air entry pressure or the bubbling pressure when you get this bend in the retention curve. All right, and we call these retention curves because it's how much water this soil can retain at different pressures. All right, so we're going to pull the pressure down even farther, and more of these guys break. And so this comes along over here. And finally, if you pull the pressure down far enough, that is, travel up this axis far enough, eventually you get to a place where the water, you just have a bunch of damp stuff left, and you can't pull that water anymore because it's not connected well enough to travel. And that is connected is actually, it's wetting the surface, right? So you can't make it move. It's like, I'm stuck to this surface here, right? And that's the irreducible saturation, all right? It's hard to measure is what this little note says. Okay. Real world dead end pockets, right? Here's water that can't go anywhere. Right? So that's why retention curves tend to look like this. They have this bit where they travel up where not much has happened. Then all of a sudden air entry pressure and you lose a lot. And then you get closer and closer to this irreducible saturation, and the curve bends up and becomes kind of asymptotic. Okay, so that's a retention curve. And this is what I mean by you look it up. We needed to look up the saturation as a function of the pressure. These variable names are slightly different, but this is exactly the same thing. You just say, I know what the pressure is, so the saturation is this. Okay, read it off the thing. In real life, you could do this with a lookup table in MATLAB, but in real life, what they do is they have complicated, ugly equations that approximate this kind of a curve. And then you can just calculate it analytically. It's an empirical equation, right? But you can just calculate what it should be. All right, so that's the retention curves, and that DSW DP term. All right, next one, oops. Here's a picture of one that says it's typical pressure head getting smaller and smaller and smaller. And here's moisture content again, but same deal, coming up here, moving across, hitting an irreducible kind of limit. Van Genuchten is famous for the equations that he generated that will give you this kind of a curve. All right, so that's why this is in here. Let's move on. How does the permeability change as the saturation falls? All right, these are also in terms of the moisture content or the water content, but if this went from 1 to 0, it would be the saturation instead. We have the same psi going up and declining as you go up. All right, so here is our retention curve. All right, and here is the curve between the hydraulic conductivity and the water content. All right, so if the water content is high, that means the pores are filled with water and the hydraulic conductivity should be high. Okay, as you start to lose water, as you go that way, right, we start to lose water, the hydraulic conductivity starts to fall because there starts to be air in the pores and it's in the way of the water. The water can't flow as easily. There's air in the way. Okay, so it comes down and it declines like that. So if you can write a curve that describes that kind of thing, you can also write a curve that describes this kind of thing. Right, so that's how you deal with those two terms that are nonlinear in the unsaturated groundwater flow equation. And these are the actual famous Van Genuchten equations. This says, what's the moisture content as a function of the pressure? All right, and we have a bunch of parameters. We have the saturated volumetric water content if we're determined to work in moisture content. All right, here's the irreducible one. And then these guys are just our parameters. This alpha, N, and M are all just these empirical parameters that you mess around with until you can figure out what you can describe your soil properly. All right, and it turns out that N, M, and alpha are all just kind of one parameter. You can calculate N from M. And once you know M, you can also calculate the alpha as long as you know the air entry pressure right there. So it's not quite as bad as it looks. And there's an equivalent expression that once you know this saturation, you can calculate the hydraulic conductivity or the permeability using these same parameters again. So that's how it hangs together. So now if you think about this sutra dealing with coupled equations and these nonlinear terms, you can see there are several things it has to do each time, but at least you could figure out how to calculate the saturation based on the pressure. There's just an equation for it, and you just use it. I think I might have another equation in there. Oh, no, these are just more retention curves for different things. Sophia, you might take a look so you remember that, you know, a sand would be a flatter kind of a thing, and a fine grained thing would be a steeper kind of a thing. But the rest of you guys, this is numerical modeling, not hydrogeology. What else is in here? There are other ways to calculate this besides Van Genuchten. You can use Brooks and Corey. And the rest of this is all optional. There's more about, oh yeah, this is a code where you could get those awful Van Genuchten parameters, which is no longer supported. This talks more about interfacial tension. If you've ever been curious about these contact angles, why your glass in chemistry has to be clean, and how, okay, yep, that's it. I'm gonna pop this out and I'm gonna stop sharing. Okay, are there any questions left over from that?
Hey, Alicia.
Yeah.
My other class was not canceled in the building and I'm still in Augusta. So do you mind if I pop out now so that I can drive to campus?
Okay, yeah. The rest of us are going to talk about the Erasmus paper just for the last 5 minutes of class.
Okay, thank you so much.
All right, have a good drive. All right, I had sort of meant to leave a little more time than just this to sort of revisit the Erasmus paper. And I know none of us have read it since the beginning of the semester. I haven't read it. I didn't warn you guys to read it. Do you remember anything about it at this point? So the main point of the paper, she was asking, what good is a model? Yeah, she was saying, what good is a model? And one of the main points was that the model was good for testing hypotheses. If the system works the way we think it does, will this happen? Right? It's not so good for reproducing reality. And at the time, that was a great concept. And that's the main point of her paper. But there were a lot of other things that happened along the way in that paper where she talked about uncertainty in parameters, for example, right? And at the time, you guys had seen like 3 PDEs. Some of you have seen more, but like you'd seen the groundwater flow equation, you'd seen the heat transport equation and the solute transport equation. And we hadn't done much of anything with any of them yet. And I know they probably still felt pretty unfamiliar. You're looking at these PDEs, this professor's going on and on about how great they are. And you're like, yeah, that's a PDE. I don't know what to do with it. Well, what you've done with it over the course of the semester is you've solved it. You solved the PDE like 3 or 4 different ways. You actually know what to do with these equations now. And I hope you have at least some feel now for how the solutions look. In solute transport, you get this front that travels, but the front becomes more and more diffuse, less steep with time as it travels because of dispersion. And you've simulated that. You've seen how the steepness of the front declines as it travels through our imaginary one-dimensional domain. Okay. And over the course of the semester, we didn't talk very much about the level of uncertainty in different parameters. I know you could tell that hydraulic conductivity varies by orders of magnitude, whereas thermal conductivity varies like by a factor of 3. So there are different things with different, if you're solving a different equation, you have different levels of variability in your parameters. But I'm hoping that what you also saw, especially just in this lecture, was how complicated the conceptual models can become for these processes. And the more complications you add in, the more, and this is where Erasmus really comes in, the more opportunities you have to mischaracterize the real system. You know what I mean? So this, I'm not going to actually make us all go back and reread Erasmus, but I want you to just remember this concept that the more complex your model gets, the more opportunities you have to make faulty assumptions, okay? And get your parameters wrong. Add uncertainty to your result, right? So one takeaway is go with the simplest model that will answer your question. If your question legitimately is, how does groundwater flow change above the water table depending on whether it's a mud or a sand, you're going to have to add the Van Genuchten or some other kind of equations in to simulate those unsaturated flow properties. You can't get away from it, right? But if you don't need to know that, don't do it, okay? And it's easy to not do it in something like Sutra. Just put your boundary conditions so you never get unsaturated flow properties, and you will have just avoided that whole question. Even though the code can do it, you don't have to use it. So So that's really mostly what I wanted to say is go with the simplest model you can. It's really tempting to go with the advanced ones because we, especially in geology and any kind of natural science, we see the variability in real life. You go out to a beach, yeah, it looks like the sand's all the same, but if you dig a little trench, you see little layers in a beach, right? So we know there's tons of variability in real life, no matter what. But simple can be very useful for testing hypotheses. Any other comments or questions before we go today? All right. Well, we have survived our first synchronous online lecture. And I can see we would get better and better at it as we go, but I think we did pretty well. What other questions do you have before we go? Anything else we need to deal with? Okay, I think the questions that are still going on are people working on their projects. So I'll get with you separately via email, or maybe we'll Zoom later. All right, thank you all. Stay dry, and I will get those recorded lectures posted for Tuesday, and we'll see you all on Zoom next Thursday. Take care. Bye.